We were chatting early this afternoon at the workshop, and I think it's the case that I've never actually made a professional visit to UCLA, although over the years I've had many friends in many different departments. So I really appreciate the opportunity to remedy that and spend a little bit of time here. It's always a pleasure and also a challenge to speak to a broader audience. And it's one that I like. I think all of us want to communicate that part of science that we're most excited about. And often the problem is that we plunge into the part that we're most excited about without having laid any foundation for the audience, and one can easily get lost. So I'm hoping to go gently for this evening, which also won't last too long. I should say that the invitation to come to the workshop, to see friends here at UCLA, those were all delightful, but the one that was impossible to turn down was to take part in the celebration of the centennial of Julian Schwinger. As Alex mentioned, Schwinger is one of the giants of 20th century physics. I had the pleasure of meeting him only once, but he had an impact on my decision to become a scientist, because when I was a high school student, there was this remarkable article which appeared in the New Yorker, which is written by Jeremy Bernstein, who's the author of many interesting articles about physics. And it was a profile of the great experimental physicist Isaac Rabi at Columbia. And Rabi was the one who discovered Schwinger, and who was a prodigy, to use an overused word, but in this case very apt. And he nurtured Schwinger's development from the beginnings of his undergraduate career at the City College of New York, transferring him to Columbia, and then arranging for him to move on to graduate school in some smooth way. Legend has it that at his undergraduate commencement exercises, Schwinger pulled out from his robes what would become his PhD thesis. So Schwinger was a legend by the time of World War II, but the thing which cemented his position in the pantheon was the work that was first announced in a 1.5-page long paper with the title up there on the quantum electrodynamics and the magnetic moment of the electron. It would be followed by a series of 3 papers which span nearly 100 pages. But this was the announcement of the result. And I want to use this as a jumping off point to get everyone thinking about what it is that we all try to do as theoretical physicists. What is it that's characteristic of physics that has been so special over these many decades? So you all know that when you plug in a light bulb into the wall, and electric current flows along the wire to the light bulb, and that's what generates the power that makes it possible to light the bulb. What some of you may know is that electrical current is the flow of lots of little tiny particles called electrons. And in fact, going into your light bulb, there's roughly 1 billion of them every second. Okay, it's a lot. What you should imagine, and what our experimentalist friends can now do, is imagine that you could trap one of those little tiny particles. So again, there's 1 billion of them in a second for a light bulb. There's fewer if you start thinking about one little transistor on the chip that's sitting inside the cell phone that's in your pocket. But still, electrons are tiny things. Imagine that you could study one of them. What you would then find out is that in addition to the fact that when they move, they carry electric current, they also act as little tiny magnets. And indeed, it is that tiny magnetism of the single electrons which eventually helps to form the magnetism of the thing that you stick on your refrigerator. By the 1940s, there was a very well-developed description of what these electrons are doing, what they do inside atoms, what they do inside a copper wire, including the fact that they acted as little magnets. But it was discovered that that little magnet wasn't quite the strength that everybody expected. It was off by a little bit. And there was a widespread appreciation that this must be due to the peculiarities of quantum mechanics. So, again, as many of you know, I mean, there are professionals in the audience, but I'm not talking to you. As many of you know, right, there's this weird thing in quantum mechanics called the uncertainty principle. So if you're watching a baseball, you can talk about where the baseball is at the moment and how fast it's moving. And that's true about a baseball, and it's true about a marble, and it's true about a speck of dust. But by the time you get down to talking about a single atom, now you have problems. And by the time and when you start talking about a single electron, it gets even worse. And so objects, what we had learned from the 1920s and 30s is that when you give a description of the truly microscopic world inside of atoms, if you know where an object is, you necessarily lose information about how fast it's moving. And one way of saying that, so that sounds sort of vague about what you can know, but you could say it in a more practical way. If you put the object in a very tiny box, so you're sure you know where it is, then it'll start jiggling around a lot. And the smaller you make the box, the more it will jiggle around. That's the uncertainty principle in action. So now you have this one electron. It can't stop jiggling around, right? Because you kind of know where it is, so it has to jiggle a little bit. But if you take a particle that has electric charge and you move it around, then you make electromagnetic waves. You make radio waves, you make light waves. And so quantum mechanics forces the world, the little microscopic world that surrounds a single electron, to be filled with these fluctuating electric and magnetic fields. And the effect of those things is to change what you see of the behavior of the electron. So if you don't look closely enough to see what's happening at the very shortest distance scale, you stand outside, then you see sort of the same electron but with different properties because there's all these fluctuating things surrounding it, like a cloud. The problem is that as of 1946, if you tried to calculate that using the tools of the time, you would have said, okay, so when the electron's jiggling around, it can make a little bit of this electromagnetic wave and it acts back and changes things, but then you could make a wave that had a longer wavelength and a longer wavelength, or a shorter wavelength and a shorter wavelength, and when you added up all the effects, you got infinity. Complete nonsense. So there was a theory, but it was totally out of control. It made nonsensical predictions. And what Schwinger was able to do, not in parallel, other people did the same thing in completely different mathematical formulations, which is one of the bizarre things about the progress of physics. What he was able to do was to show how to reorganize our thinking about these complicated interactions at the very shortest distance scales in such a way that you could pull out a finite answer and say that the net result of all this complicated fluctuations was that that electron would act like a tiny magnet, but the strength of the magnet would be different than you expected by a part in 1,000. And that agreed with the experiments. At the time, it agreed perfectly with the experiments. And of course, this wasn't the only thing you could calculate. You could do all sorts of other things. But that was the one that, for Schwinger, was the one that put the stamp and said, now we understand. I can calculate something that's the end result of all these complicated processes that I always knew were there. It wasn't that he imagined things that no one had ever imagined. It's that he understood how to tame all of that complexity and pull out something that you could see in experiments. Now, if it was an experimentalist standing here, that person would tell you the wonders of how it's possible to measure something to 1 part in 1,000, which, you know, that's a good story too. By the way, this calculation is usually expressed in a slightly different this result is usually expressed in a slightly different symbolic form, in which a very particular constant that describes the charge on the electron appears, divided by 2 times pi, the same 2 pi that relates the radius and the circumference of a circle. And that form is what's carved on Schwinger's gravestone. Now, in 1948, that was the state of experiments, and that was the state of the theory. And they agreed. Today, we now know that that 6 is 596521807.3. The 7.3 has a little bit of uncertainty in it, give or take about 28. Now, here, I don't know whether it's the theorist's story or the experimentalist story that's more remarkable. This is the most accurate measurement in science. Full stop, okay? There's nothing else that competes with it. And using the same mathematical structures that Schwinger laid down, we can calculate what this number should be, and it agrees all the way out to here. So, I think when people write the history of science 150 years from now, this extraordinary accomplishment of having theory and that you can measure something to a part in a trillion, and you can calculate what that is, a property of the real world, okay? The fact that we can make that measurement, that we can do that calculation, and they agree with each other, will be one of those milestones where we say, that was a moment where we achieved mastery over some part of the universe. It's a small part, but it has lots of consequences. This number is so astonishing that I think we need some perspective. And so I'd like to show you another number. You'll notice that this number has suspiciously zeros in it. And that's because this is not a number that you can measure quite so accurately. This is the gross domestic product of the United States in dollars. 19 some odd billion. 19 trillion, sorry. You'll notice that the number of digits is the same. So one way of thinking about where Schwinger's great accomplishment has led us is it's led us to a theory of at least a small part of the world. By the way, electrons are in every single atom, right? So it's a small part of the world in one sense, because we're only talking about one electron, but it's a composition of everything in the universe, or everything, at least everything in the terrestrial world. We can calculate the behavior of a single electron with a precision which would be the equivalent of predicting the gross domestic product of the United States to an accuracy of $1. And remember, all the electrons are alike, so you have to do that every year. So, Schwinger's approach was very formal and emphasized mathematical beauty. And I think that's a great inspiration that he's given to subsequent generations. But it's worth remembering that the end result of all that mathematical beauty is you compute something about the real world to this extraordinary accuracy. So that's the business of theoretical physics. We try to give a mathematical description of the world around us, which is compelling in its way, so that by the time I finish, I feel like it couldn't be any other way. And yet, when I apply that beautiful, all that mathematical beauty to the real world, I actually get the right answer. And that combination is the joy that we all take in this enterprise. Of course, this wasn't a new idea. It goes back to Galileo. My accent in Italian is not good enough to reveal in public, But this is usually paraphrased as saying that the book of nature is written in the language of mathematics. It's a little more interesting. So first of all, you'll notice that what we would now call physics was then called philosophy. So there's interesting history there. It's written in a great book that constantly lies open in front of our eyes. I'm speaking of the universe and so on. It ends by noting that if you don't learn to speak the language, you're condemned to wander in an obscure labyrinth, which is some great punishment. So 300 and a bit years later, in his Nobel lecture, Schwinger phrased it this way, describing mathematics as the irreplaceable instrument for the penetration of realms of physical phenomena far beyond the ordinary experience on which our language is based. It's very beautiful. So what we do is we search for mathematical descriptions of the world, but it's the real world we're trying to describe. Let me make one more note about Schwinger before I get on to business. And that is that he had another feature which is incredibly inspiring. And that is that perhaps uniquely among the great physicists of his generation, he was a remarkable teacher in very particular ways. He gave flawless lectures, flawless to the point where no one asked a question. And we can discuss whether that's a good way to teach or not, but they were everyone agrees they were flawless, and no one, I believe it is reported that someone remembers somebody once asking a question and they were ignored. He worked with a succession of PhD students who in total numbered 72. At his peak, there were more than 2 students who were finishing every year, getting their PhDs and going off to jobs. Famously, 4 of these people won Nobel Prizes. It's not the only thing you want to measure, but it is pretty, I mean, by the time you've got 72, it's almost like doing statistics, right? You can say, you know, your odds are 1 in, never mind. What's particularly interesting is if you look into the details, you'll discover that these people won their Nobel Prizes for doing completely different things. So the inspiration that they took from Schwinger, they all agree, not just them, but most of the people who have been interviewed agree was essential to their development as scientists, yet they all went off into completely different directions. A demographic note, so at Schwinger's 65th birthday, by which time he was already here at UCLA, there was a symposium to celebrate, and some of the students got back together. You'll notice there are not 72 people there. It's a little blurry, but you may notice that there's one woman. Your colleague, Margaret Kivelson, in Planetary Sciences, who will be 90 later this year. Anyhow, so with this inspiration from Schwinger, let's look around, not at the behavior of single electrons in a box, not at the expanding universe, not at the amazing properties of the new materials that people can make in the physics laboratory. Let's look at the world of living things. And you see all these strikingly beautiful phenomena. Flocks of birds that on the one hand are very ordered, but seem somehow fluid and flexible. Bats that can hunt their lunch, this little moth here, by using sound, right? They emit ultrasonic pulses and listen for the echoes, and they use that to find where they build an image of the world around them and find the objects that they want to eat. It turns out, by the way, that their system for doing that is so precise that they can resolve the time it takes for the sound to go out and come back, the delay in the echo. They can resolve that not to 1,000th of a second, which you might have thought was reasonable because that's the time scale of basic events in the nervous system, not to 1,000,000th of a second, which you might have thought is the right answer because if you're listening, for example, if you close your eyes and ask where the sound is coming from as I'm speaking, if I move around a little bit, and you ask, what's the smallest movement that you can detect? That corresponds to a change in the time between your two ears of about a millionth of a second. But the bat can do 100 times better, and it can resolve times to 10 billionths of a second. These are experiments like the ones that we were hearing about during the workshop today, where you're looking at the cells in the brain in the region that helps this animal figure out where it is in space, and you see these remarkable patterns of cells turning on and off. Of course, there's the often beautiful body plans of particular organisms. This is the caterpillar of a particular moth, where you see these gorgeous segments. And this is the complicated dance of the cells in the embryo of a fly as it starts to turn itself from being a ball of cells into a structured object. So during the course of embryonic development, there's a remarkable thing that has to happen. You start with a ball of cells, and a ball of cells has an outside and an inside. The problem is that the grown-up animal has two outsides. There's this one, and then there's this one, right? And, well, we're sufficiently isolated from meal times. If you think about it, you realize that this outside goes all the way through you. You have to make this astonishing transition from something that has one outside to something that has two outsides. And actually, this is the moment at which that's happening. It's a very complicated dance. So can you imagine taking all of this, and you know, this is just some random selection of phenomena from the living world, right? I could go on and on. If you're sitting in a dark room or you're looking on a moonless night, then your visual system is so sensitive that it can respond to individual quanta of light arriving at your retina. When you're sitting in a quiet room and you can just barely hear a sound, your eardrum is vibrating by the diameter of an atom. Okay? And on it goes. And actually, those aren't the ones most biologists would choose. It's because I'm a physicist, I find those sort of cool. Can you imagine having theories of these phenomena that not have the part in a trillion accuracy that we have with the magnetic moment, right? That's never going to happen. But can we have something like that, where we have mathematical structures that are powerful enough to capture this complexity in a way where we can really calculate something and get it right? So that's the thing that my colleagues and I spend our time worrying about. And at least for me as a theorist, that's the challenge in trying to do the physics of biological systems. Can we get to the point where we have theories in the sense that we know, we use that word in physics, where we have this extraordinary ability to calculate and get the right answer? So let me give you a classic example. And that's the eyes of insects. Now, unfortunately, the reproduction of this photograph is not so good. I encourage you sometime to sit very quietly and look at the head of a fly. And what you will see is that there are lots of little, well, you may not realize it, but there are little lenses on the surface of the eye. And they form a beautiful pattern. Now, the fact that there are many lenses is at first confusing, and it makes you think that their eye must be very different than ours. Gary Larson has been retired for a number of years, and so he's perhaps not as familiar to some of you as he once was. He very seldom got things so systematically wrong in describing the biological world. Just because you have lots of lenses doesn't mean you get lots of copies of the image, okay? This is not the last thing that a fly sees. In fact, in some ways, a fly's eye is not so different than ours. In our eye, we have the surface of the eye, the thing on the outside, right? The place where you put your contact lens, if that's what you wear. There's a lens right underneath. The reason you need the contact lens is that that's not doing what it's supposed to do. And then in the back of the eyeball, there's your retina. And in your retina, there are little cells that absorb the light and generate a little electric current, just like in your digital camera. In the fly, and its relatives, other insects, it works slightly differently. Instead of all the cells looking out through the same lens at the outside world, again, like in your camera, each cell has its own private lens and looks out at a little part of the world. Okay? Now, that immediately raises a question. How big should the lenses be? Oh, by the way, why do you do this? Well, you see, it's great to have a really big lens because big lenses make for better images, as you'll see in just a moment. But the problem is that there's all this empty space in between. And for us, this isn't the problem because we're pretty big animals, so we can afford to carry around all this empty space. And if you weren't sufficiently disgusted by the discussion of how many insides you have, I will remind you that the size of the fly is the size of this empty space. That's really something you don't want to contemplate before dinner. But it's true. So if you're the size of a fly, you just can't afford to do this. No matter how nice it would be to have this big lens, you don't have the space. So you're forced to do something which we in technology have learned to do more recently, which is to put all of the optics into this very thin layer. So how should you design the fly? How should you design the eye? Well, so there are many jokes about physicists' love of simplified models. One of them ends with the punchline that you've worked out the case of the spherical horse. So in this case, we're not going to do a spherical fly, but we're going to do a spherical head, which is a much better approximation. You can do better than this, but for the sake of discussion, if your head has a radius r, and you make your lenses of size d, then the angle that you've basically divided the world up into little pixels whose angular size is just the ratio of these two things. And in this point of view, what you say is, oh, make the lenses as small as you can, pack in as many pixels as you possibly can, right? When you go and buy a digital camera, you pay more for more pixels, right? So that must be better, right? This is America. We know that if it costs more, it must be better. And so put in more pixels, make D smaller and smaller. But that's not the whole story, because it turns out light is a wave. And if you try to put a wave through a small hole, it bends. So you can do this experiment in your bathtub. Now, the people who did this one, it was slightly fancier than a bathtub, but trust me, you can do it in your bathtub. Imagine that you put your hand in the bathtub and you move it up and down through the surface of the water. As you do that, waves will start to propagate along the surface. And that's what you see here. Here are the waves. And somebody's been very careful to make sure that the thing they're moving up and down is not their hand, but a nice wide nice wide paddle, so that it produces a very orderly set of waves. And this set of waves propagates, but then it comes to a small hole. And when it comes to a small hole, the waves bend. Now imagine that you were sitting behind this small hole and seeing the world with these waves. Well, despite the fact that you're in this small hole and you only think you're looking in this direction, the waves can reach you. So imagine running the whole thing backwards. The waves can reach you from all the way over here. And that means that looking through this small hole, you see this blurry view of the world. So now let's think back to the insects problem. If he makes the lenses very big, then he just doesn't have enough pixels. And so his view of the world is in these big, coarse pieces. On the other hand, if he makes the lenses really tiny, then this blur due to what's called diffraction, the effect that I was just showing you, takes over and causes you, although you've got lots of pixels, they're all overlapping with each other, and so you don't really get any extra image. The compromise is to go in between, and that corresponds to a simple formula, which you perhaps don't want to think about, but you all learned this in high school, right? So you take the radius of your head, you multiply it by the wavelength of light, and you take the square root. And that gives you the best size for the lenses. So the fact that diffraction was a problem for the insect eye was realized in the 1890s, not long after the theory of diffraction was worked out. this calculation that I show you here actually makes an appearance in the undergraduate lectures by Richard Feynman, Schwinger's great rival, who notes that if you do this calculation and you apply it to a bee, a honeybee, you get the right answer to within 10%, and he goes on. But it turns out that 10 years before Feynman, Horace Barlow, who is a historical note, it's Darwin's great-grandson, he did this calculation, and he went into the drawers in the Zoology Museum in Cambridge, England, and he took out lots of insects and measured the size of their head and measured the size of the little lenses. And then he plotted the size of the lens versus the square root of the size of the head. And sure enough, it works pretty well. Now, this isn't as precise as even Schwinger's 1948 calculation, but we're making progress. This is kind of not a part in 1,000, but maybe 10%. Okay? And you'll notice that we just used our understanding of physics to try and see why the biology is organized the way it is. So what I'd like to do now, which entails some risk, is to tell you about a problem that my colleagues and I have been working on for several years, where we think we see signs of being able to calculate with this kind of precision. But I emphasize, we see signs. So I'm going to tell you about, in what I'm about to tell you, there are parts that I'm absolutely certain of, and there are parts which we're still arguing with the referees at the journal. And I'm doing that not because I'm hoping that I'll get around the referees and you'll all be convinced, but because I want to convey to you the state of excitement in the field and the things that I'm excited about at the moment. And the risk of that is that the things I'm excited about at the moment could eventually turn out not to be true. But I hope you'll see at least what we're trying to do. And well, stay tuned. You'll find out whether we're right or not. So what's the problem? The problem is that beautiful striped moth caterpillar that I told you about. Turns out all insects have these segments to their body. Actually, we also have segments in our body. Think about your spinal cord, right, with the stack of vertebrae. That's more complicated. Let's think about insects. It's easier. And you might ask yourself, how does, as the animal is developing inside the egg, how does one part know to be orange and the other part know to be black? And how does it know where to put the little spikes that are coming out and so on? So there's a remarkable discovery, which is that at least in flies, it's easiest to see this in flies. If you stop the action, about 2.5 hours after the egg has been laid, you just stop everything. How do you stop the action? To be honest, you gently cook the egg. Gently, not to mix everything. Don't scramble the egg, just gently cook it. So everything stops. All the molecules stop moving. You can do a little extra chemistry to tie everything to everything else so that nothing will move. And now you say, let me see if I can attach a colored label to one particular kind of molecule. And the way you do that is you make antibodies against that molecule. And then you attach a label to the antibody so that the antibody, wherever it goes, it's colored. But it only sticks to this particular molecule because that's one of the amazing things about our, so you exploit another amazing part of biology, which is the wonder of our immune system, that it responds very specifically to particular molecules in the environment. So normally we're responding to, the flu virus or something. In this case, what you've done is to take a particular molecule out of the fly, inject it into a rabbit, and the rabbit will make antibodies against that molecule, and you take those out. Very good. And then you color one of those molecules, one of those antibodies, you color it green. And another one you color orange. And what you see is stripes. And in fact, there are several other molecules that you could have picked that also make stripes. and they sort of interleave with each other in a way similar to what I've shown you here, but if I showed you them all at once, it would be complicated. So I'll just show you two. At the moment where you can see this, no cells have moved yet. Everything's sort of staying still. But this cell knows that it should be part of the green stripe, and this cell knows that it should be part of the orange stripe. And it turns out that if you came away from this lecture and you thought, oh, these stripes, they're like those stripes, that's not so far off. It's not exactly right, but it's very close. So what that means is that 2.5 hours after the egg is laid, you can see a blueprint for the plan of the body. So that doesn't tell you how it all works, but it does tell you that if you're interested in how you build a complicated body, you can say, well, part of the problem has already been solved after 2.5 hours. It takes a whole day in a fly for the egg to hatch. Or it takes only a day for an egg to hatch, depending on how you think about it. Some of you perhaps have had to suffer through the 9 months that we're stuck with, so a day sounds pretty good. But 2.5 hours, nobody's moved, and these cells already know what they're supposed to do. So what would it mean to have a theory of this, right? Oops. Well, you look in the biology books, and they'll tell you that they kind of understand how it works. So the things that I was just showing you were these genes that were these molecules that come in stripes. And the molecules that you're looking at here are proteins, and the proteins are coded for by DNA that's organized into genes. And so one tends to describe these as being genes, although what you actually measure is the protein. This is one of those language problems. And there are lots of these things that make these nice stripes, 7 stripes, each one. And you ask, well, how do they know where to make the stripes? And the answer is, well, there are these other molecules that have some more sort of softer patterns, right? This one's on over here and on over here, kind of fades out in the middle. This one has a patch over here and a patch over there. This one just has a stripe in the middle, but a kind of wide stripe, right? This stripe is, And somehow these things all together turn on this pattern. And how do these guys know what to do? Well, in proper Freudian fashion, it's the mother's fault. When the mother makes the egg, she actually marks the ends of the egg so that there are other molecules whose concentration is high where the head will be. There's one molecule whose concentration will be high, that'll be high where the head will be, and gradually falls off as you move toward the middle. There's another molecule whose concentration is high where the tail will be and falls off as you move toward the middle. And then there's a third molecule that's high, whose concentration is high at both ends and low in the middle. So this is a little bit like if you're walking in a building where they've painted the floor to help you find your way. Except in this case, it's not that they painted the floor blue so you go to the cafeteria and yellow so that you go to the office. Here, it's how dark the blue is tells you how close you are to the cafeteria, right? And that starts up here and works its way down until you get these stripes. And what are these molecules doing? Well, what these molecules are doing is they go and they stick to a very small piece of DNA, and they control whether that piece of DNA gets read out to make more molecules. So actually, in some sense, they don't do anything. They just turn each other on and off. And that's what all these arrows are supposed to mean. Now, I've got 3 things that turn on 4 things. These guys can turn each other on and off, and then eventually they turn on these 3 things. This looks incredibly complicated. So how on earth and actually, if you actually read the chapters of the biology book in which this appears, trust me, it really is very complicated, and even this is an oversimplification. So how on earth can I imagine getting to a theory of this that's anything like what we're used to in the rest of physics? So I need a hint about what to look for. And the hint is that this process is incredibly precise. So you've already seen this movie, and I want to draw your attention not to all this rearrangement over here, but to what happens over here. So the very first step, actually, and the difference between that ball of cells up there and this group of cells down here is 15 minutes in the life of the embryo. And in those 15 minutes, the embryo has drawn a line here, which you see here. So we stopped it just at the right moment. And this is going to become the head of the fly, and this is going to become all the rest of the fly. So this is the neck, right? Which has the grand name cephalic furrow. It's a neck. And if you go back to those pictures that I showed you before, what you'll find is that this line is drawn right at the boundary of one of those green and orange stripes. So the way you know where to draw the line is those green and orange molecules. So here you're looking at the embryo from the side. What I want you to imagine now is that you're looking down on the embryo from the top, and with your microscope, you focus on the middle of the embryo. And in the middle of the embryo, all the cells are on the outside, right? The inside just has yolk. It's an egg, after all. All the cells are on the outside, and this cephalic furrow that you see is forming here as the cells come inward. But now, you can do this experiment not on one embryo, but on 100 of them. And if you look carefully, what you discover is that, I'm sorry that the reproduction is so bad. If you look carefully, what you find is that when you line them up, this point where the furrow comes is the same in every embryo with an accuracy of 1% of the length of the egg. And if you count how many cells there are, how many rows of cells there are from this end to that end, you'll find that it's less than 100. So what that means is that cell number 34 knows that it's supposed to go in the head, and cell number 36 knows that it goes in the rest of the body, and cell number 35 knows it's the neck in every embryo. Extraordinarily precise. So how is it? This is the sort of thing that, as a physicist, makes me very suspicious. Right? How on earth is this possible? In fact, you get more suspicious the more you know about how it works. So I told you that there are these molecules that the mother has put in where she marks the part that's going to be the head. And indeed, if you look carefully, so this is one of these fantastic experiments that one can do now. This is done by my colleague Thomas Greger. You genetically engineer the fly so that whenever it makes this molecule, instead of making the molecule it normally makes, it makes that molecule with a fluorescent tag attached to it. And as a result, when you shine light on the embryo, it glows back at you, and the brightness tells you how many of these molecules there are. And if you look carefully, you find that all these molecules are inside the nuclei of the cells, and there are more of them at the head than there are in the middle. And if you could imagine blowing it up, what you would discover is that two cells that are right next to each other, like the one that's going to be in the head and the one that's going to be in the neck, the difference is 10% in how many molecules there are. But there are only about 1,000 molecules altogether. So you could say, I don't know, I can count to 1,000, and I can count to 900, and that difference is 10%. And I can tell the difference between 1,000 and 900. What's the problem? Well, the problem is that there's no way for the embryo to stand outside the nucleus and look in and count all the molecules. What has to happen is that those molecules have to stay inside the nucleus and go do something to the DNA. So let's think about what they do. They go and they stick to some little tiny spot on the DNA. So this is kind of hard to imagine, so let's blow things up. Let's imagine that the whole nucleus was the size of our neighborhood, so 1 kilometer across. Then the target that they're looking for on the DNA is 0.5 meter, which is the width of a person. So the job that the cell has is it's as if you wanted to know whether there were 10% more students on campus this year than last year. And of course, the easy way to do that is go to the registrar's office, but you can't. The only way you can do it is to stand there and wait for the people to walk past you. And if they run into, and count the number of them that run into you, or get close enough that you would count it as running into you. And you realize that it's going to be kind of hard to get an accurate estimate of how many students are on campus just by doing this, right? And it's worse because the students, at least in most of the week, tend to walk in reasonably straight lines, whereas molecules move around at random. So you're standing there and these things are, now imagine people are moving around at random and you're trying to count them just by waiting to see if they run into you. Well, if they moved around faster, that would help because you'd see more of them. If there were more of them in some way, it would be easier, right? Because you see more individuals. And if you could count for longer, then that would also be easier because you get a better sample, like taking a census or something. But you can translate those arguments into what's going on with the molecules. And what you discover is that, of course, if I give you only a certain amount of time and there's only a certain number of molecules and they only move around at a certain speed, which are the properties of real molecules, then there's a limit to how accurately you can tell whether they're 10% more or less. And the limit is that you can tell whether there's 10% more or less, but you can't do any better. So the fly, by being able to have two cells that are right next to each other decide, I'm going to do different things in response to these signals, is coming very close to the limits of what the laws of physics allow just from counting the molecules as they randomly move around. So maybe that's the essential hint to understanding how this works. Maybe the way all this complicated machinery is set up is to try and squeeze as much information as you can out of that limited number of molecules as they move around randomly. So let's imagine that the only signal you had was this molecule that shows up in the middle. So if you only have this signal, so the way you're looking at this is, okay, so how do you turn this into numbers? Well, you plot as a function of position from the head to the tail, how bright is this, which tells you how many molecules there are. And so you get something that goes up and it comes down. But this isn't the question. The question is, if you're a cell and you feel a certain concentration of these molecules, do you know where you are? So that's the same as sort of turning this thing sideways, right? What I do is I measure how many of these molecules I see, and I ask, do I know where I am? And you realize, just from looking at the picture, if you measure a very high concentration, you know you're somewhere in the middle. If you measure a very low concentration, you don't know much. You could be anywhere in this front half or this back half. And actually, it's a little more subtle than that, because if you measure something in between, then you don't know whether you're on the leading edge or the falling edge. So if you only had this molecule, you'd be terribly confused. If you were a cell sitting here, you wouldn't know anything about where you were. Well, you know you're not in the middle, but you could be anywhere. If you're a cell right in the middle, you're pretty sure you're in the middle, but actually, you don't know that precisely. There's a whole range of places you could be. And if you're on these lovely flanks, you're very sensitive because this slope is very steep, so you can tell whether you're here or here, but of course, you could also be here or here, so you're a little confused. But fortunately, in the picture that I showed you, you don't just have one of these molecules, you have four of them. And by the time you put all four together, then those pictures get a lot better. If you're a cell that's sitting here, and I ask you to use all the information that's contained in those four molecules, four different kinds of molecules, you can figure out where you are, and your error bar is indeed 1%. So we can show by direct analysis of the experiments that these molecules carry enough information to tell a cell where it is to within 1% of the distance from one end to the other, and that is how precise the whole system is. But, and this is the place where, you know, Schwinger's apology for speaking in the language of mathematics is relevant. I'm not going to speak in the language of mathematics. I'm going to try and tell you what's embodied in that mathematics. It's not only that I can tell you that there's enough information to get to 1% accuracy. it's also true that if you analyze those experiments, you can figure out, in some sense, you can make a lookup table that says, if I see a high concentration of molecule number 1, a reasonably high concentration of molecule number 2, none of molecule number 3, and a low concentration of molecule number 4, I must be 30% of the way from the head to the tail. And then all the other combinations. So I can make that whole table just by analyzing the experiments. So I can build that mathematical structure. And the principle behind building it is use all the information that's available to you. So we imagine that this problem of telling the difference between being one cell and the cell right next to it is so difficult that evolution has pushed the mechanisms that are operating inside the embryo to be as efficient as possible in extracting this information. But these are flies. And there's generations of experiments in which people have studied mutations in flies. In fact, the way we know that these are the molecules which are relevant was a remarkable series of experiments done by my colleague Eric Wieschaus and his collaborator Janine Nusslein-Volhard in the late 1970s, where they made mutations in flies by feeding them terrible chemicals, by exposing them to X-rays, and they looked for mutations that affected the body plan, where they could see, sometimes even in the embryo, that something had gone wrong. And they did this again and again and again, and what they found was that there were only 100 genes that were relevant. That meant, you notice that I only had, 1, 2, 3, 7, 8, 9, something like a dozen different kinds of molecules in the picture for making the plan along the length. That's the result of that experiment. That whole body plan is laid out as a result of the interactions among, dozens of molecules is a big number, but it's not infinite, right? It feels like something you ought to be able to understand. So let's use one of those mutants, and let's use the one where you knock out one of those signals that the mother puts in at the beginning. And then that changes everything all the way through. But remember, what we said is that information flows from the signals in the mother to these intermediates to making the stripes. And I told you that if I read out the information from here, I can determine where to put the stripes, or I can determine position with 1% accuracy. And so I have a theory of how this readout works, which is driven by the principle that you extract all the information that's available. So now let me use that theory to read out the signals at this level, not in a normal fly, but in a mutant fly, in which one of those signals at the top has been knocked out. And in this particular mutant fly, if you're a cell sitting here, and you look at those 4 molecules, you think you're here. So everything's fine. You put the stripes in the right place. But if you're a cell sitting out here, you're a bit confused. The concentrations of all those molecules, if you use the rules that we learned for squeezing out all the available information, it turns out that you're a little confused. You actually think that you're further away from the tail than you really are. And again, this is a theory in the spirit of the theories that we started with, right? This is not descriptive. We actually can write down the equations that do this. But if you're a cell that thinks it's here, well then you should make a stripe. And so let's look and see what happens. You make a stripe. And similarly here, if you're here, you think you're a little bit off, but then you should make another stripe, and you do. And actually, remember, there are 7 stripes, normally. You'll notice that because the map that you make is distorted, now you only make 6. And in fact, in some cases, you only make 2, and you get that right. My favorite one is the one where this stripe is actually missing, And if you look at the map, it has these funny distortions, and then it has a piece that kind of goes the wrong way, where the cells that are closer to the head actually think they're closer to the tail. And correspondingly, it makes this stripe over again over here. And you can show that it's not this stripe moving, it really is a copy of this stripe. And, well, you can go on. There's lots of stripes. There's 3 different signals at the top. So you can knock them out one at a time. You can knock them out 2 at a time. You can test these ideas on something like 70 different stripes. And it works every time. There's actually one that we get wrong. We think we know why. In fact, you can do better. Remember I told you everything's accurate to 1%. In the mutants, if you do this, and you go through this argument of decoding the information that's contained in these signals, you find that these stripes should jiggle around. And sometimes they should jiggle around much more than they do in the normal fly. And then you look in the mutants and they do jiggle around. And in fact, sometimes you find that this map intersects the stripes, and sometimes it doesn't. And so that means that in some of the embryos you find a stripe, and some of them you don't. And you get that right too. So, as I say, this is work in progress. It's the result, it's where we are in a collaboration that's been going on for a decade. There's been many steps. I've had the pleasure of collaborating with Eric Wieschaus, the guy who discovered all these molecules, with Thomas Greger, who began as a student with us and then went off and came back as a faculty member, and now runs a lab that really pushes the techniques for doing these experiments ever more precisely. Remember, think back to what I told you about at the beginning with Schwinger. It's not that Schwinger calculated this correction to the magnetic properties of the electron just for fun. There was an experiment that said the numbers were off from what we expected. And that's what stimulated everybody to think much harder about the theory. It's not that once you measured the number, you knew the answer, but you knew there was a problem. And so theoretical progress is linked to experimental progress, right? If you don't measure anything interesting, there's nothing to calculate, right? So our improved ability to make measurements on these biological systems has revealed a whole another layer of beauty, sometimes complexity, but most importantly, to me at least, precision. And this is an example of that precision, this business of being able to lay things down with 1% accuracy. And the work that I'm describing actually a crucial part of this. So, as I say, Tomas was a student and is now back in Princeton as a faculty member. Eric has been our collaborator all along and a great teacher in the subject. Gasper was a student with us and now a professor in Vienna. And Mariella was an undergraduate when she did these experiments. It's taken us a long time to understand the experiments, so she's almost finished with her PhD somewhere else now, but still, she did this when she was an undergraduate. It's quite an amazing body of work. So, I hope that the somewhat long introduction about Schwinger told you a little bit about why he sits in this special place in the Pantheon, that you see the inspiration that the work that he and many other people have done gives to us to have a sense of what it means to have a theory of the natural world. It really is extraordinary that we can calculate things about the world and get them right with that kind of precision. I hope that you have a sense for the beauty of the biological world, which is maybe a little different than you had when you walked in, and that you see that we have gotten to the point where we at least have glimpses of places where we can actually calculate to the point where we capture some of that beauty. So, thank you very much.